up till now, we've talked about magnetic fields that are constant or uniform. We've talked a little bit about the patterns of those fields, but we haven't really talked about what happens when they change, in particular when they change as a function of time. So I'll set up a little example for you, and we'll have a demonstration to talk about this in more detail. But let's say you have a bar magnet like this, and you know that it produces a magnetic field everywhere in space. If you bring a loop of wire near that bar magnet, nothing happens. Nothing happens to the wire. Nothing happens to the magnetic field. Maybe they're sort of attracted to each other because this is ferromagnetic or whatever. But you know, you can sort of like control for that. But when you start to move the magnet around, so let's say we move it towards that loop of wire, what we find is that that loop of wire will develop a current running through it, one that we can actually measure. We can put you know, some multimeters on it, and we can actually determine that there's a current running through it. So as this magnet moves sort of in towards the wire, it develops a current that runs around the wire. Now this is just an observation. It's something that Faraday investigated in some detail, and what was found was that the faster that you move that magnet, the larger the current that you develop in this situation. So basically, how quickly you move this magnet around determines how much current you get. A stronger magnet will produce a larger current moved at the same speed as a weaker magnet, if you will. And a loop of wire that's larger, will produce a larger current as well. It depends on how the scale of that loop of current is around the magnetic field. So if you make it too big, the magnetic field outside is very, very weak. So up to some sort of point, you can sort of see how the strength of the magnetic field and the loop of wire, the properties of the loop of wire rather, give you some sense of how big that current would be. Now it turns out that this is all related to sort of a complex phenomena that we're going to unpack in a couple of videos, that moving magnetic sources, right? So things that produce magnetic fields, when those change, they actually generate an electric field, and that's what's going to drive this current. But what we're going to relate this to is this idea of magnetic flux, because this gives us a way of actually determining or calculating what's actually going on here. So that magnetic flux is going to be this integral over some surface of the magnetic field. So in this case, if we're looking at this situation, it would be the flux through this loop. Now, I know what you're probably thinking is that, well, didn't we say that there's no magnetic flux? Right? When we look at sort of a closed volume, we look through that surface, there's no magnetic flux because there's no magnetic monopoles. And you're right, that's exactly the case. But this is a different situation in that this is not a closed surface, it's an open surface. There's only one side. If we made it closed, that is, made a big bubble that went all the way around it, that's absolutely right. There'd be no total magnetic flux through that closed surface. But through this open surface, where we're not enclosing the entire bar magnet, we're fine. Okay? So this relationship here, this magnetic flux that we're observing, is directly related to the potential difference that develops in this wire. And so we're going to use that to understand what kind of current is driven. But the relationship that we're going to end up working with is that the change in the magnetic flux over some period of time, again, how quickly that happens, is going to be related to an induced potential, right? That is, this is a result of not batteries and so forth. It's an induced result that is caused by this new, strange-looking electric field that's going to show up. The minus sign here takes into account the fact that the way that the current develops is to oppose a change in flux. And we'll talk a little bit that in some detail as well. Why does that happen? How does it generate it in that way? But the current that it develops is to produce a magnetic field that opposes the change in magnetic flux. So all we've done in this video is just kind of briefly talk about this observation that we have, which is that when we start to move bar magnets around, and when magnetic fields start changing around some wire or coil, we develop these currents. And this is going to be related to this idea of the magnetic flux and how it changes with time. And the details are going to be a little bit more complicated than we've presented here. There's some relationship with the electric field that is developed as a result of this. But for now, what we want to do is understand that this is just an observation, and we're going to try to model it.